What if our first hint of life beyond Earth doesn't arrive with trumpets and headlines, but as a quiet pattern in starlight, a soft, steady whisper from a world wrapped in hydrogen, glowing under a gentle red sun? Imagine a planet where day never quite becomes night, and the air carries the slow rhythm of chemistry that refuses to rest. Quick note before we drift in. If deep, cinematic science helps you unwind, please subscribe. We're pushing for our first 1,000 subscribers so we can make more videos before your sleep. Your click genuinely helps us keep going. This story centers on K218b, circling a small, steady star about 120 light-years away. It's larger than Earth, more like a mini Neptune than a rocky twin, yet its atmosphere keeps showing ingredients that make scientists lean a little closer. Methane, carbon dioxide, and patterns that, on our world, often point to active cycles instead of a quiet chemical stalemate. You may have seen the bolder claims hints of sulfur compounds that, here on Earth, are tied to biology. They sound exciting, and they are. But as you settle in, it's okay to let the urgency go. Numbers like 3 sigma are not a verdict. They're an invitation to keep looking. Instruments have moods. Stars have spots. Models disagree. The careful path is patient. Check alternatives. Gather more light. See if the pattern persists. So this won't be a sprint to proof. It's a slow, mindful walk through evidence building. We'll drift with the James Webb Space Telescope as it reads a planet's air by watching starlight pass through it. Tiny dips at precise colors, like notes in a lullaby, sketching an atmosphere we may never touch. We'll hold what's clear, acknowledge what's debated, and rest with the possibility that a hydrogen-rich Hycean world might widen our idea of where life can take root. If we're lucky, the first truly living sky we recognize won't look like home at all. It may be crimson and layered, clouds moving like breath in a warm room. And that's the point. Life may not prefer a copy of Earth. It may prefer balance. K218b circles a small red star in the constellation Leo, about 120 light-years away. The star is cool and quiet compared to our Sun. Its light is softer, more ember than flame. The planet completes a lap in roughly 33 Earth days, close enough that one face may always lean toward the star, like a sunflower that never turns away. K218b is larger than Earth, about the size we call a sub-Neptune or mini-Neptune. That name matters. It hints that the planet is not a bare rock, but something dressed in layers. A core, perhaps some water-rich material, and a broad envelope of light gases such as hydrogen and helium. Its mass and size together suggest a world with room for weather, clouds, and chemistry. Room for an atmosphere thick enough to tell us stories. We learn those stories by watching starlight during transits, the moments when the planet slips across the star from our point of view. A tiny portion of that light passes through the planet's air before reaching us. Different molecules nibble different colors, leaving a faint barcode in the spectrum. From Earth, that difference would be invisible. From space, with the James Webb Space Telescope's steady gaze. So far, the clearest lines in K218b's barcode speak of methane and carbon dioxide, simple molecules that, together, point to an active atmosphere rather than a frozen or exhausted one. Earlier work with other telescopes had already hinted at water vapor. Webb sharpened the picture and gave us more confidence in the pattern. There are things we don't know, and it's gentle to admit them. We don't yet have a photograph of oceans, only possibilities suggested by models. A hydrogen-rich world might host layers where temperature and pressure feel surprisingly mild, windy regions where droplets form and fall, and lower layers that grow warm and dense. Somewhere in that stack, conditions could resemble a temperate day on Earth, at least for a while. But could is the right word to sleep beside. It keeps the mind open and the heart unrushed. Think of K218b as a book we've just begun. A few pages translated, many chapters still sealed. The lines we can read are intriguing, and the font is getting clearer with every transit. The rest will come with patience and more light. A star emits light across many wavelengths. When K218b moves in front of its star, a thin portion of that light passes through the planet's atmosphere before it reaches the telescope. Certain gases absorb specific wavelengths, leaving small, repeatable dips in the spectrum. Reading those dips is how we infer which molecules are present. With K218b, the James Webb Space Telescope has found the most consistent evidence for methane, CH4, and carbon dioxide, CO2, in a hydrogen-rich atmosphere. Earlier observations with other facilities also pointed to water vapor, and JWST's data are broadly compatible with that possibility, though details continue to be refined. Taken together, these findings indicate an atmosphere that is active and layered rather than thin or chemically exhausted. A hydrogen-rich envelope tends to form broad cloud and haze layers. In many models of sub-Neptune worlds, heat from the day side is redistributed toward the night side by winds, smoothing temperature differences. That behavior can mute extreme weather and create pressure-temperature regions where common molecules remain stable and detectable. For K218b, retrievals that fit the data well typically include a dominant H2 background gas, measurable CH4 and CO2 absorption features in the near-infrared, clouds or hazes that slightly flatten some spectral features rather than erasing them. Another helpful clue is what the spectrum doesn't strongly favor. Some simple atmospheric scenarios predict prominent ammonia, NH3 features. Current JWST fits do not require strong ammonia to explain the data. This absence is not a proof of anything by itself, but it is consistent with an atmosphere that is mixed and processed over time, instead of drifting into a simple equilibrium dominated by NH3. It's important to keep the scope clear. Transit spectroscopy does not deliver a photograph of a surface or ocean. It constrains gas abundances, cloud properties, and temperature profiles that, together, describe a likely atmospheric state. For K218b, that state looks like this: a large planet with a deep, hydrogen-rich atmosphere where methane and carbon dioxide are present at levels high enough to leave clear, repeatable signatures in JWST's infrared bands. Uncertainties remain. Spectral retrievals depend on assumptions about clouds, temperatures, and laboratory barcodes, opacity data for each molecule. Different teams test different assumptions to check robustness. As more transits are observed across a wider range of wavelengths, error bars should shrink, and any model dependence will become easier to evaluate. In short, the solid part of the K218b picture is a hydrogen-rich atmosphere with detectable methane and carbon dioxide, likely accompanied by clouds, hazes, and results that are consistent with earlier hints of water vapor. This is already an interesting outcome for a sub-Neptune world and a strong reason to continue observing it carefully. A star shines across many wavelengths. When a planet passes in front of it, a small fraction of that light filters through the planet's atmosphere before reaching the telescope. Molecules in the air absorb specific colors. In the data, those colors show up as shallow, repeatable dips. By matching the pattern of dips to known molecular barcodes, we infer which gases are present and in what rough amounts. For this work, the James Webb Space Telescope observes in the infrared, Where common atmospheric molecules have strong signatures, multiple instruments help. NIRIS, NIRSpec cover shorter infrared wavelengths, sensitive to features from methane, CH4, water, H2O, and other light molecules. MIRI extends to longer wavelengths, useful for checking consistency and separating similar-looking features. A standard observing run has 3 simple stages. Before the transit, measure the star's light as a baseline. During the transit, collect light that has passed through the atmosphere. After the transit, compare with the baseline to isolate the atmosphere's imprint. The spectrum you get is then passed to retrieval models. These models vary the atmosphere's temperature structure, cloud and haze properties, and gas abundances to find combinations that best reproduce the observed pattern. A few elements guide this process. Clouds and hazes can soften specific features. Retrievals test whether muted lines are better explained by aerosols, by different temperatures, or by lower gas abundances. Temperature profiles influence line strengths and shapes. Warmer layers can deepen or flatten certain features. Opacity databases, laboratory measurements of how molecules absorb light, provide the reference barcodes. Good lab data make better fits. Stellar effects, spots, faculae, can slightly color the stellar light. Models account for these, so the planet's signal isn't misread. The goal is convergence. Independent reductions, different instruments, and multiple transits, all pointing to a consistent atmospheric picture. For K218b, the most stable result so far is a hydrogen-rich atmosphere showing methane, CH4, and carbon dioxide, CO2, at detectable levels. Prior work suggested water vapor. Webb's measurements are broadly compatible with that, pending more refined constraints as additional transits are analyzed. Some simple scenarios that would predict strong ammonia, NH3, features are not favored by current fits. What this method does deliver: probabilistic estimates for key gas abundances, evidence for clouds, hazes, and an approximate sense of where they sit, bounds on temperatures in the layers that shape the spectrum. What it does not deliver: a direct image of surfaces or oceans, a single exact composition without model context, instant certainty from one transit or one wavelength band, because different combinations of gases, clouds, and temperatures can sometimes produce similar spectra. Degeneracy: the field relies on broad wavelength coverage and repeated observations. Consistency across NIRIS, NIRSpec, MIRI, plus agreement between independent teams using different retrieval approaches increases confidence. If a feature persists across instruments, epochs, and processing pipelines, it is likely real. If it fades with more data or changes with reasonable modeling choices, it is treated cautiously. In practice, the process is incremental. Each transit tightens error bars or shows where a model should be adjusted. Over time, the atmosphere's description becomes less flexible, and the set of plausible compositions narrows. For K218b, that description presently supports a layered, hydrogen-rich atmosphere with CH4 and CO2 clearly present and H2O plausible. This is already a valuable result for a sub-Neptune. It shows an atmosphere with active chemistry and structure, suitable for continued study with future transits and complementary facilities. Among the many gases that scientists hope to read in an exoplanet's air, dimethyl sulfide DMS gets special attention because, on Earth, it is closely tied to marine life. That's why K218b drew headlines when some analyses suggested its spectrum might slightly prefer a model that includes a sulfur-bearing molecule like DMS or a related species. The fair summary is calmer than the headlines. The evidence is a low significance preference in certain wavelength ranges, the kind of result that tells researchers to keep looking, not to declare a detection. Different teams, using different modeling choices, have reached different conclusions about whether a sulfur component is truly required by the data. That split is exactly what keeps the discussion open. The reason this remains unsettled starts with the way we measure these atmospheres. We don't collect a sample of air. We watch starlight pass through it and look for tiny, repeatable dips at specific infrared colors. Those dips are compared to laboratory barcodes that tell us how strongly each molecule absorbs light. When the wavelength coverage is limited or the signal-to-noise is modest, several molecules can mimic one another's shapes over narrow bands. That is spectral degeneracy, and it's common. Add the fact that K218b likely has clouds or hazes that flatten features, plus temperature changing with altitude, and you end up with many plausible ways to reproduce the same small dip. One retrieval will lean toward a sulfur species, another will get a similar fit by shifting temperatures, cloud heights, or the allowed set of gases. If a feature appears or fades under small, reasonable adjustments like these, confidence stays low. Everything stands on the quality of the laboratory data as well. The barcode's opacity line lists must be accurate at the temperatures and pressures relevant to hydrogen-rich sub-Neptune atmospheres. For some sulfur species, those data are still being refined. Gaps or uncertainties in the line lists can quietly tilt a retrieval toward or away from a sulfur solution without anyone intending it. As laboratory measurements improve, a suspect feature can move. Sometimes a fit that seemed to favor DMS settles on a more mundane molecule. Other times, a weak possibility becomes clearer. Instruments and stars can complicate things too. Even well-calibrated spectrographs imprint tiny, color-dependent systematics. Cool stars like K2O-18's host can have star spots and bright regions that change the apparent color of the star during a transit. If those effects aren't modeled carefully, they can masquerade as atmospheric structure. The standard remedy is straightforward. Collect more transits, observe in additional wavelength regions, reduce the data independently with different pipelines, and check whether the same feature persists. Real atmospheric signals recur across instruments and epochs. Artifacts usually do not. Suppose that, after those checks, a sulfur feature does become more convincing. The next step is not to jump straight to biology, because K218b's chemistry is likely governed by a hydrogen-rich envelope with different rules than Earth's. Under those conditions, non-biological pathways can produce sulfur compounds. Volcanic outgassing from the interior, photochemistry driven by the star's radiation, and delivery by small bodies are all possible sources. The question then becomes quantitative. Can known abiotic processes supply the inferred amount of sulfur and maintain it alongside the observed methane and carbon dioxide without generating other spectral features we do not see? If the answer is yes, the biological interpretation weakens. If the answer becomes difficult across multiple models and constraints, interest grows, but only as fast as the evidence allows. What would nudge the sulfur story from interesting toward compelling is not a single number. It is a set of consistencies. The same signatures should appear in independent wavelength regions, for example, both the near-infrared and the mid-infrared, at abundances that agree with one another. They should repeat across different instruments and across multiple transits, within the stability we expect from the atmosphere. Independent teams should retrieve similar results even when they vary priors, temperature profiles, and cloud assumptions. Statistical comparisons should clearly favor models that include the sulfur species over models that exclude it. and that preference should survive when the model space is widened to include reasonable alternatives. Finally, the full composition has to make physical sense. The temperature-pressure structure must allow the molecules to exist where the spectrum forms. The planet's energy budget must balance. Cloud layers must sit where they can, given particle sizes and vertical mixing. And the ratios among methane, carbon dioxide, water, ammonia, and any sulfur species must fit a self-consistent climate chemistry picture. The strength is in the pattern holding together across these checks. There are equally clear ways the sulfur idea could fade without drama. Additional data might reduce the statistical preference once the model space is broadened. Updated line lists could attribute a suspected feature to a better-known molecule. A signal that seems present in the near-infrared might fail to appear where it should in the mid-infrared at the same abundance. Or independent pipelines might not recover the feature under reasonable choices about clouds and temperatures. Any of those outcomes would steer the community toward non-sulfur explanations. The near-term plan reflects all of this. Teams will gather more transits to raise signal to noise and test stability. They will expand wavelength coverage to break degeneracies and check crossband consistency. They will run independent reductions and retrievals, comparing results under different priors and cloud prescriptions. Laboratory groups will refine sulfur opacities at relevant temperatures and pressures so spectral fits rest on firmer ground. Observers will also look at similar sub-Neptunes to see whether any sulfur-like pattern repeats elsewhere or is unique to K218b. Comparative context often clarifies what a single target cannot. Against this backdrop, the sturdy parts of K218b still stand. A hydrogen-rich atmosphere with methane and carbon dioxide clearly indicated, results compatible with water vapor, and no strong requirement for ammonia in current fits. The possible sulfur component sits outside that core as a live question. It may become a meaningful piece of the puzzle. It may settle into the background as the data and models improve. Either way, the process is doing exactly what it should, moving from hints to tests, from tests to patterns, and from patterns to conclusions that survive new information. That is why the fairest line to use today is simple and precise. An interesting hint under debate. The coming seasons of spectra, models, and lab measurements will determine whether sulfur earns a place in the story of K218b's atmosphere or quietly steps aside for a cleaner explanation. Hycean is shorthand for a planet with a hydrogen-rich atmosphere and potential liquid water conditions somewhere in or beneath that atmosphere. K218b is often placed in this conversation because its spectrum points to hydrogen as the background gas and shows clear methane and carbon dioxide signals that fit models where the air is layered, mixed, and chemically active. The question is not whether this guarantees life. It doesn't, but whether such an environment could support it. Start with structure. A sub-Neptune like K218b likely has a deep envelope of H2, He above heavier material. The interior might be rock and metal, or an ice-rich layer that under pressure forms high-pressure phases of water, ice 7, X or supercritical water. Between the upper low-density atmosphere and the compressed interior, models often produce a temperate band at intermediate pressures. Not too hot, not too cold, and dense enough to form cloud decks. That band is what transit spectroscopy is most sensitive to, and it's where chemistry we understand can operate for long periods. Heat distribution matters. Around a cool red dwarf, many close-in planets are tidally locked. One hemisphere faces the star, the other is in perpetual night. A thick hydrogen envelope moves heat efficiently from day to night. smoothing extremes. General circulation models for these worlds produce broad jets and overturning cells that carry warmth, vapor, and photochemical products around the globe. In practical terms, this can create long-lived, mild layers in the atmosphere where temperatures and pressures fall into familiar ranges, regions that do not require a solid surface to host stable droplets or aerosols. Chemistry in hydrogen atmospheres looks different from Earth's, but it is not empty. Methane is common in reducing environments and can be both produced and destroyed by photochemistry. Carbon dioxide provides a counterweight as an oxidized reservoir. Ultraviolet light from the star breaks some molecules apart, forming radicals that drive chain reactions and haze formation. Complex hydrocarbons. Vertical mixing can then shuttle these products between bright, photochemically active altitudes and darker, warmer layers where different reactions dominate. The result is a cycle slow, persistent, and capable of maintaining gases out of simple equilibrium. Where might life fit in such a cycle? Two broad possibilities are discussed in the literature. 1. Aerial niches in the atmosphere. If a temperate layer exists where pressures are on the order of tenths to a few bars and temperatures are moderate, suspended microenvironments could persist. Droplets, aerosols, or porous dust acting as chemical scaffolds. On Earth, microbe-sized particles and spores can remain aloft for long periods. In Venus studies, researchers have explored the idea of aerial microbe analogues in temperate cloud decks. K218b would differ. No sulfuric acid clouds are expected, but the general notion is similar. Patches of liquid or semi-liquid material renewed by condensation and evaporation, offering surfaces, gradients, and reaction partners. A hydrogen-rich atmosphere would not supply free oxygen, but many anaerobic metabolisms do not require it. Hydrogen itself is an energy currency in a wide range of terrestrial microbes. Redox pairs involving carbon, nitrogen, or sulfur could in principle power chemistry in a reducing sky. Dose interfaces deeper down. If there is an ocean-atmosphere interface anywhere in the column, whether that ocean is water-rich, water-ammonia, or dominated by supercritical phases, chemical gradients at this boundary can be strong. On Earth, hydrothermal vent systems show that life can organize around redox gradients with minimal light, using chemical energy from water-rock interactions. On a sub-Neptune, the details would change, pressures would be far higher. Solvent properties could differ, but gradients are the key, not sunlight. If liquid water contacts minerals, water-rock reactions, for example, serpentinization-like processes, could generate hydrogen and other reduced species that, in turn, feed larger cycles. Whether such contact exists depends on the interior architecture. Some models keep high-pressure ice layers between any ocean and the rocky core, limiting water-rock reactions. That uncertainty is central. The presence, depth, and composition of any ocean layer remain open questions. Energy, supply, and stability set the practical limits. Red dwarfs can flare, producing bursts of UV and particles, but a dense hydrogen envelope is an effective UV shield at depth, and tidally locked circulation spreads energy around. If the host star is relatively quiet, the system may enjoy long, steady epochs in which chemistry is allowed to run without frequent resets. That kind of stability favors complexity. On the other hand, persistent high-energy irradiation could drive vigorous photochemistry that destroys certain molecules faster than they're supplied, raising the bar for any metabolism that depends on them. Both outcomes are plausible. The star's activity history and the planet's magnetic environment, unknown matter. Nutrients and building blocks are another constraint. Carbon clearly exists in multiple forms, CH4, CO2. Nitrogen's partitioning is less certain. The apparent lack of strong NH3 in current fits neither proves nor rules out nitrogen availability, because nitrogen could hide in N2, HCN, or aerosols that are harder to detect at low resolution. Phosphorus and metals, vital trace elements on Earth, would likely come from interior outgassing, dust, or meteoritic infall. In a hydrogen-rich sky, many minerals are less volatile. Actual delivery pathways are model-dependent. This is a reminder. Detection of bulk gases is only the first step. Life depends on trace chemistry as well. It is also necessary to separate habitability of an atmosphere from habitability of a surface. K218b may not have a conventional surface accessible to the atmosphere at all. If high-pressure phases isolate the interior, any deep biosphere would be sealed away from the sky we observe. In that case, ARIEL niches become the leading candidate, and the search strategy shifts to gases that are most likely to be produced and released within the atmosphere itself. Conversely, if a pathway exists between atmosphere and liquid layers, exchange processes, evaporation, aerosol injection, wave breaking could loft biosignature gases upward where transit spectroscopy can see them. What we don't know is as important as what we do. The C/O ratio impacts dominant hydrocarbons and oxygen-bearing species. The bulk metallicity sets the strength of many features. The mean molecular weight influences scale height and thus spectral depths. Cloud composition remains uncertain. Candidates include water, clouds, and photochemical hazes, each with different optical properties. Three-dimensional circulation, unsteady weather, and patchy clouds can all bias one-dimensional retrievals if not accounted for. These uncertainties are resolvable, but only with more wavelengths, more transits, and independent analyses that test sensitivity to assumptions. Even with these caveats, the case for possibility is straightforward. Hydrogen-rich atmospheres can maintain temperate layers. K218b shows signs of a dynamic, mixed atmosphere, and reducing environments support rich organic chemistry. None of that proves biology. It does put K218b in a category where life is physically discussable rather than purely hypothetical. If future spectra reveal a suite of gases in stubborn disequilibrium repeating across instruments and epochs, and the combined climate chemistry model can't reproduce that suite with known abiotic pathways, then a Hycean world like this becomes a serious candidate. Until then, the careful statement stands. K218b is a promising laboratory for hydrogen-rich climate and chemistry, with plausible niches that deserve attention and clear unknowns that must be narrowed. The next observations will tell us whether those niches are simply good theory or something more. Confirmation is not a single measurement. It's a stack of consistent results that leaves little room for alternatives. For K218b, that begins with repetition. A feature suggested in one transit must reappear in later transits with compatible strength. It should also show up where physics says it belongs in other wavelength regions. If a molecule leaves a mark in the near-infrared, its lines in the mid-infrared should be visible at the same abundance within uncertainties. Cross-band agreement trims away many false positives. The next layer is cross-instrument coherence. Independent detections with JWST's NIRIS, NIRSPEC, and MIRI build confidence because each instrument has different systematics. If a feature persists across them, the odds of an instrumental artifact drop. Independent data reductions should reach similar conclusions even when they use different pipelines and noise models. When results converge despite different methods, what remains is likely real. Retrieval robustness is a third filter. Atmospheric fits that return the same composition under reasonable changes to priors, cloud prescriptions, and temperature structures are more trustworthy than those that only work under one narrow setup. Statistically, models that include a candidate molecule should be preferred over those that exclude it by clear margins, and that preference should hold as the model space is broadened to include plausible alternatives. In practice, teams look for outcomes that stay put when knobs are turned. Physical realism closes the loop. The inferred gases must live inside a climate that balances energy and chemistry. A temperature-pressure profile should allow those molecules to exist and persist at the altitudes where the spectrum forms, without demanding contradictory conditions elsewhere. Cloud heights, particle sizes, and vertical mixing rates must be consistent with the same model, a composition that looks good spectrally but fails. Basic physics does not count as confirmation. All along, abiotic explanations are tested quantitatively. Interior outgassing, photochemistry under the host star's radiation, and external delivery are modeled to see whether they can keep the same gases at the same levels without creating lines that are not observed. A biosignature case strengthens only as these non-biological scenarios become difficult to sustain across bands and epochs. Beyond JWST, several facilities can turn interesting into compelling. Extremely large ground telescopes, ELT, GMT, will use high-resolution spectroscopy to resolve individual lines and measure wind patterns and line shapes, helping to separate overlapping species and check for isotopic signatures. ESA's ARIEL will survey hundreds of exoplanet atmospheres, providing comparative context useful for deciding whether K2-18b's pattern is common or exceptional. NASA's Nancy Grace Roman Space Telescope will expand the planet census and demonstrate advanced coronagraphy, a step toward routinely separating a planet's light from its star. Farther out, starshade or next-generation coronagraph missions would capture a planet's own light directly, rather than relying only on transits, opening new spectral windows and phase-dependent information about clouds and heat transport. Each of these adds an independent angle on the same question. There are also system-level measurements that help. Refining the planet's mass and radius narrows the mean molecular weight and scale height, which sharpen abundance estimates. Better characterization of the star, its spot coverage, flare rate, and ultraviolet output reduces stellar contamination in the spectra and tightens photochemical models. Laboratory work to improve opacity on line lists, especially for sulfur and nitrogen species, at relevant temperatures and pressures, reduces model uncertainty at the most basic level. How strongly a molecule should absorb. In the best-case path, the picture becomes simpler, not more complicated, as data accumulate. The same set of gases appears across bands and instruments. Abundances settle into tight ranges. The climate model closes its energy budget. Independent teams reproduce the result, and abiotic models struggle to match the full pattern without contradictions. That is what confirmation looks like in exoplanet atmospheres. A stable story told by multiple data sets, methods, and physical checks. K2-18b matters even if no biosignature is confirmed, because it reshapes where and how we look. For years, the default target for life was an Earth-sized planet around a sun-like star with liquid water on a rocky surface. That template is still valuable. But surveys show that sub-Neptunes are far more common, and many orbit long-lived red dwarfs. By revealing a hydrogen-rich atmosphere with clear molecular features, K2-18b demonstrates that these worlds can be measured with precision and modeled in detail. It widens the map of promising environments beyond a narrow set of Earth analogs. The planet also refines the method. Instead of chasing a single magic molecule, the field is moving towards suites of gases measured across multiple bands and epochs, tested against physically consistent climate chemistry models. K218b is a live example of that approach. Methane and carbon dioxide form a stable core result. Water remains plausible. Ammonia is not required. Sulfur-bearing candidates are kept provisional until broader coverage and better lab data settle the question. This is a disciplined template other targets can follow. There is a strategic shift in instrumentation too. K218b shows the value of pairing near-infrared and mid-infrared observations and of repeating transits to narrow uncertainties. That encourages programs that allocate time for multi-band, multi-epoch coverage rather than one-off snapshots. It also supports investment in laboratory spectroscopy for molecules that have lagged behind, especially sulfur and nitrogen species, at the temperatures and pressures expected in hydrogen-rich atmospheres, because better line lists turn ambiguous features into decisive tests. Comparative context is another gain. As more sub-Neptunes are observed with the same playbook, patterns will emerge. Which stars foster certain chemistries, how common temperate layers are under hydrogen envelopes, and where clouds most often sit. With a larger sample, the community will be able to separate unusual one-offs from typical behavior, making any future biosignature claim less dependent on a single planet's quirks. Finally, K218b clarifies communication. It shows that audiences can follow a careful, step-by-step explanation that distinguishes between robust results and debated hints. That sets a healthier norm for future discoveries. Share what's firm, label what's tentative, and show exactly what additional data would move a claim forward. Clear standards help the science and the public trust it. In short, K218b expands the search space, sharpens the methodology, motivates specific measurements, and builds a roadmap for comparative studies, whether or not it hosts life. It makes future confirmations more likely by teaching us how to look and how to decide. Discovery is only half the work. The other half is how we choose to live with it. A planet like K218b invites a kind of humility. It reminds us that life, if it exists elsewhere, may prefer chemistries and climates that don't resemble our own. That realization shifts the story from, "Are we unique?" to, "How do we fit?" Curiosity stays, but the posture changes. Less conquest, more connection. There are practical consequences. If repeated observations ever point to biology, even in the most modest form, the way we explore must reflect care. Current space law was written for an era that assumed lifeless rocks and empty space. A living atmosphere, or even a plausible one, asks for updated norms, protecting alien ecologies from our contamination and protecting our own world from theirs. That doesn't mean we stop exploring. It means we explore with boundaries, clear protocols for what we touch, what we release, and how we share what we learn. A second consequence is closer to home. The same models that help us understand hydrogen-rich climates teach us about Earth's feedbacks, how gases regulate temperature, how clouds alter energy flow, how fragile balance can be. Studying distant worlds can sharpen our judgment about this one. If an exoplanet can maintain stability for long stretches, it shows that equilibrium is achievable under the right conditions, and that systems can be resilient or brittle depending on inputs we can measure and manage. There's also a cultural dimension. Claims about life beyond Earth can amplify noise or elevate signal. K218b is a case study in pacing. Say what the data support. Keep an open file on what's still being tested, and explain the path from hint to confirmation so people can follow along. That approach builds trust inside the field and with the audiences who fund, watch, and care. Finally, discovery reframes purpose. If life is common, our place isn't central. It's participatory. The value of our telescopes and probes isn't that they put us above other worlds, but that they connect us to them. The patience required, repeat the transit, widen the wavelength, check. The model becomes part of the meaning. It says knowledge is earned. And when we earn it together, we're less likely to mistake excitement for evidence. K218b may never give a definitive answer about life. It may simply teach us how to ask better questions, how to compare atmospheres fairly, and how to separate patterns from coincidences. That is still progress. Wonder opens the door. Wisdom decides how we walk through it. K218b is not an Earth twin, and that's the point. It shows that promising environments can look unfamiliar. Hydrogen skies, layered clouds, chemistry in motion. Webb has given us steady pieces, methane, carbon dioxide, a hydrogen-rich backdrop, and a clear path for what comes next. More wavelengths, more transits, tighter models. No single line decides the story. Patterns do. If a biosignature is ever confirmed here, it will be because multiple gases hold together across instruments and time, and because simple, non-biological explanations fail. If not, we still gain something essential, a sharper method and a wider map for the worlds that follow. Either way, the search improves. Don't forget to subscribe and hit the like button. The signal from K218b is still being tested. The standard is the same as always. Measure, repeat, compare. Let the evidence decide. And when the pattern is ready, we'll be here to lay it out. No rush, no noise, just the story the data can support.